Welcome to this video presentation, Constrained Random Verification for FPGAs in VHDL. My name is David Clift and I'm an applications specialist for FirstEDA. FirstEDA is a value-added distributor of electronic design automation solutions in Northern Europe, specializing in software and hardware solutions for electronic design and verification. I'm joined again today by Jim Lewis, the founder of SynthWorks, principal architect of the open source VHDL verification methodology, better known as OSVVM, as well as being chair of the IEEE VHDL standardization group. Welcome back, Jim. It's nice to have you with us.
Hi, David.
As we discussed in our previous videos, one of the biggest challenges facing FPGA design engineers today, working on large FPGAs and small, is how do they verify their completed designs to prove that they function in the manner that's required. In this presentation, we will look at constrained random verification, which seems to be in the press a lot these days. Can you explain to me, Jim, what an engineer needs to do to apply this technique to his design? It sounds to me as if it's a fix for all my possible problems with verification. Is that true?
It always sounds that way. Yeah, so what I hear out of the community that promotes constrained random a lot is that everything can be done with constrained random, and we simply tweak the constraints to get it to do this and that. That's not the way I see it at all. I see constrained random as one of the tools in our toolbox. Okay, so I see one of the more critical tools in our toolbox to be transaction level modeling, which we talked about last time. From that, we can build anything, whether it's a directed test or a constrained random test or any a file-based test or any other form of testing. So constrained, again, constrained random is one of the tools in the toolbox. Additional tools you need: functional coverage, self-checking, comprehensive error reporting. Okay. So I've kind of mulled over your questions that you had for me, and kind of threw down some topics that we should talk about when we talk about constrained random. And the first is why randomize? Okay, so that should be your first question whenever you're asking anything, is why am I doing this? Is it really going to be better than what I was doing before? Next, we'll look at what is in the OSVVM randomization library. How do I take that library and make constrained random? And now once I've got constrained random, how do I tell when my test is done?
That's a good point. You could leave something running forever.
Yeah, exactly. Okay, so the first question we should be asking is why randomize? Okay, so let's take a look at a FIFO test. So if we do a directed test of a FIFO and we track the number of words in the FIFO, in fact, that's what this diff count is. Diff count is the number of words in a FIFO. And when we're looking to test a FIFO, we basically want to fill it up, see that it's working, empty it, see that we successfully empty it, put words in it, read and write simultaneously. We want to fill it all the way up and test that we don't overrun it, empty it, and test that we don't underrun it. Okay, and this first trace is an analog trace of the number of words in the FIFO. Okay, so first we fill it up. You can see that on the left of the green line there. At the top, it's full. And then we empty it. And then when it hits the bottom, it's empty. And then we take it up to the midpoint and we run it for a while. So we're reading and writing at the same time. And then finally, we fill it up and we try to write more words. And we fill it up and try to write more words. And that's those next three peaks in there. And then we run it for a while at the midpoint. Then we empty it and try to read one more word. And we empty it and try to read one more word. And we do that a couple of times also. And if we take a look at our test plan, we can certainly check off all the boxes in our test plan. Okay. Now, on the other hand, if we write a random test for this, okay, and put some constraints on the random test about filling and the number of idle cycles, okay, so we can control the rate at which it fills, we can control the pauses between bursts of traffic. All right. Now we're still looking at diff count, but we also need to look at some additional signals. We need to track, did we actually do something interesting? So this read empty and write full, read empty detects a read while the FIFO was empty, and then write full detects a write while the FIFO is full. Okay, and then we count those. And basically this test decided I want to see 100 of them. And then it just ran the test. And you can see not only do we hit the endpoints, and you can see that we're also incrementing our coverage monitors here, that we're also running through the middle space pretty well and wandering around the space really well. So not only does this hit all the requirements of my test plan, but this also wanders the space better than the directed test does.
Yeah, looking at that, Jim, it looks much more like the usage I'd expect of a FIFO in a finished design in the real environment. So
Right.
it's a nice test.
Right. And then what you have to think about is, what do I randomize? Okay, I randomize values, modes, operations, and sequences. And this is ideal for when we're generating a large variety of similar items. Ethernet packets of different flavors. And that sort, networking in particular, is really, really well suited to constrained random methodologies here. And the big benefit here is we generate realistic stimulus in a timely fashion. Now, keep in mind, what does timely fashion mean? It means to write the test, because studies have shown that test writing is consuming the time, and we have plenty of platforms to run simulations on. Okay, so a constrained random test doesn't run faster than a directed test, okay? But it has the huge potential to be more thorough than a directed test. Okay, so my metric then is, if it's not faster to write or more thorough to use constrained random, then use another method. There's nothing wrong with directed testing. It's just about, you need to be using the most effective method to get your verification job done now rather than a month from now.
Yeah, Jim, you mentioned earlier, the different testing methodologies are basically tools in the engineer's toolbox. So you've got constrained random, directed tested, file-based testing. And I think it's part of the skill of the engineer to select the right tool for the right job.
Oh,
It's a bit like the old adage, you can't put a screw in with a hammer. Well, you can, but you make a mess of the job. So you want the right tools for the right job.
Absolutely. I like that analogy. Okay, so in OSVVM, everything is built on top of our randomization library. Okay, so our randomization library includes utilities to randomize a range except skip some values. So that's the 5 and 11. That's actually an integer vector parameter there. Randomize a set. And again, here we represent a set as an integer vector, a single integer vector parameter being passed in. And then a set with exclude values. Now, exclude values with a set, when it's just static values like this, doesn't make a lot of sense. Okay, but when we're saying randomize the set except exclude the last two values that were generated, that makes a lot of sense. We can do weighted randomization, where we specify the weight that we want. The values that we get back in order, when it's a constant value parameter here, will be 0 through n-1, where n is the number of items in your array here. So we have 3 items in an array. It's going to return either a 0, a 1, or a 2. So basically, to determine how often one of these happen, we sum up all the values. So these values sum up to 10. And the first value will happen 7 out of 10 times, or 70% of the time, roughly. Okay. The second, 20%, and the third, 10%. We also have another method that allows us to specify both a value and a weight. Okay, so this first one, the value is 1, the weight is 7. The next value is 3, the weight is 2, next value is 5, the weight is 1. So again, we have a ratio of 70% at a time, 20% at a time, 10% at a time, setting it up the same as the previous example, except taking control of what values are returned. Okay, by itself, this is not constrained random. This is just randomization. Okay, so to create constrained random on top of this, we're going to use some code. Okay, so our code, we take our dist-int, our distributed case, and we're creating 70% at a time, we're generating a 0, and that'll correspond to our nominal test case down here. 10% at a time, we'll be generating a 1, which might correspond to a different test case. So the first one, we might be doing UART traffic. So the first one might be generate no errors. The second one might be generate a parity error. The third one might be generate a stop error. The fourth one might be generate a stop and a parity. And the fifth one might be generate a break error. And what I'm doing here is I'm setting up operations, data values, and then once I get down here, I'm going to send them to my transaction subprogram. So I'll do UART send with that data value and with that operation. Okay, so this becomes my constrained random operation. And when I have transactions like this, I can either do my transaction here at the end, or I can do my transactions within the case statement itself, whichever makes the best sense. Me, I'm just trying to write the simplest, most readable code. So here then again, the randomization plus the code plus the transaction calls, this is what makes our constrained random test. Now, the next interesting question that comes along is, how do I know when my test is done? Well, this happens for any complex, any design of any complexity. As the complexity grows, how do I know a test did what was intended? Okay, so this obviously applies to constrained random tests because we really don't know what the test is doing. We know what the test is doing, it's not really constrained random. Okay, but with directed tests, how do I know the test really did what was intended? Well, I have to have a way to determine when I'm done. And there's two common methods. One is code coverage, and the other one's functional coverage. So first, I'm going to pick on code coverage a little bit. Code coverage is a simulator collected metric on what has been run. Okay, but the problem is when we have a concurrent language that runs many iterations, delta cycles, per clock cycle, we're not getting an exact measure anymore. Because what we're really trying to measure is what was executed just before the clock cycle. Okay, so what code coverage is going to do for us is it clearly identifies what has not been run. Okay, so it clearly identifies holes in our testing, but in my mind it's optimistic, one, because it runs on delta cycles. The other problem with code coverage is it only ever reasons about things that are in the code. Okay, so if you're trying to bin things, if you're wondering, did I do everything in my test plan? Well, it can't answer that problem, because if you were required to have 3 counter timers in your design and you only have 2, code coverage isn't going to tell you that. Okay. Functional coverage, on the other hand, is user-written code that observes the test plan executing. Okay. So when a test plan has been completely executed, then we're done. Okay. And we'll explore functional coverage a little bit more in the next session. So kind of summarizing, constrained random tests can reduce the time it takes to develop tests. However, keep in mind that constrained random is just one tool in the verification toolbox, and other methods include directed testing, algorithmic testing, file-based testing, and intelligent coverage randomization, which we'll kind of talk about a little bit in the next section.
Thank you, Jim. That's most enlightening, and I can see, just running constrained random stimulus generation isn't enough. If you're using that tool out of the toolbox, you need to be also looking at functional coverage as well. And as you mentioned, we'll be looking at that in our next video presentation. Well, Jim, as always, it's been a pleasure being with you today, and I look forward to being with you again soon.
Thanks for having me here, David.
That's a pleasure. Thank you for joining us in our discussion. Watch out for the next video discussion when we'll be covering functional coverage techniques. If you require further information, please visit our website at www.firsteda.com. Thank you for joining us.